Welcome back, everybody. In this video, I'm going to be talking about how to apply tolerances and geometric controls to threaded features. So there are threaded features all over engineered parts, and typically the ones that I work on are internal threads, and that's mostly because cap screws or similar fasteners are used to hold parts together. And Y14.5, geometric controls apply to the pitch cylinder by default. And because a pitch cylinder is a feature of size, material modifiers can be used, and should they is a question that I'll talk about in a little bit. And I'm also going to give my 2 cents about the idea of threads being self-centering, because I do see a little bit of conversation about this online. Let's look at some terminology. Major diameter, minor diameter, flank, and pitch are all physical components of the thread, but what's not a physical component is the pitch diameter. And the pitch diameter is an imaginary cylinder generated at the point where the thread width is equal to the space between the threads. So if you take half the pitch and look at that on either side, you generate the pitch diameter. And the axis of the pitch diameter is where geometric controls are being applied. Looking at methods to inspect threads, there are ways to inspect the diameters of the pitch diameter, major diameter, and minor diameter. The most common thing that I think QA shops have is go and no-go gauges, so they don't actually give you a measurement, they just say if it's in spec. But there are interesting gauges to inspect, for example, the pitch diameter. Some other things I'd like to point out is that we have ways to measure location and orientation of threads. By installing a gauge into a thread, you can inspect a cylinder that is projected outside of the surface with a CMM, and then the CMM operator can either project that axis into the part or out of the part. And something else I'd like to point out is that there doesn't seem to be an easy way to inspect the major diameter on an internal thread, and keep note of that because we'll talk about that in a little bit. Now, why do some people say that threads are self-centering? And I think the easiest analog to look at is that of a cone. If you were to take a cone and pull it with a force along the axis of the cone into a mating part, and the surface friction between the two parts was such that it could be overcome by the force, those two parts would center on each other. But let's say there's some sort of side load or a moment on that cone. Well, then you might imagine that there's like an angular offset, or if there's a physical block, a distance offset between the axes. And how does this apply to threads? Well, a rough approximation could be to say that a thread is just a series of stacked cones. And maybe in that case, then a better statement is to say that a thread is self-centering under a load coaxial with the axis of the pitch cylinder. And where would this side loading come from that we should see in real life? Because of course, no force is perfectly coaxial with an axis. So where would this side loading or moment come from? One option would be interference, and I think that's what would most likely create that distance offset between two axes. And I don't really want to take this too seriously, because most of what we do in the stack-ups for GD&T is to prevent physical interference. That's like kind of the whole point. So we can kind of ignore this a little bit. What we can't ignore is that angular offset, and that could come from something like joint face angularity. And joint face angularity, it would be the idea that the part being clamped by the fastener is not perfectly perpendicular to the axis of the threaded hole. And this is something that's important to think about, because if you're doing a high load cyclic activity, maybe like a really large pressure swing on a pressure vessel, every little bit of angle that you have offset between the head of the bolt or screw and the axis of the thread drops the life of your joint significantly. So if you look at this chart, below 1 degree, your number of fatigue cycles just plummets. Now is probably a good time to talk about how I would go through my default tolerancing process for a threaded feature. So my default is typically to use RFS and a projected tolerance zone, both for location and sometimes for orientation, if that it's a high load cyclic activity. So let's look at an example. Let's say we've got two parts. The lower part is maybe some very expensive part that we don't want to scrap ever. The upper part is super cheap and we've got tons of them. They're easy to make, not too worried about it from a production standpoint. The threaded features we're using are M6 and the clearance hole is an MMC size of 8 millimeters and the mating part is 14 to 15 millimeters tall. So the first thing I'll do is I'll use the fixed fastener formula to figure out how much total locational tolerance I have to work with. So in this case, the MMC size for the hole is 8 millimeters. The MMC size for an M6 thread is 6 millimeters. 8 minus 6 is 2 millimeters of positional tolerance that I can allocate to each hole feature. And because I said that the lower part is really expensive and difficult to make, I'm going to give it the bulk of the positional tolerance. In this case, I'm going to give it all 2 millimeters of positional tolerance, and the clearance hole has a large size tolerance, so I'll say it's got 0 at MMC positional tolerance. And we'll say that's related to datum. Maybe there's some other datum structures in there, but for now we'll just look at the surfaces. So I can't quite apply a positional tolerance to the M6 threads yet because we want to project that tolerance zone the length of the mating part. So the mating part, the MMC height is 15 millimeters. So that means we will project that 2 millimeter tolerance zone 15 millimeters off of the surface. And because this is a high load application, I want to make sure that the orientation, the allowable orientation relative to the surfaces is, under that 1 degree limit that I'm setting. In this case, we're going to assume that the mating part, the orientation of the surfaces are perfectly parallel to each other, so we're going to ignore them in the calculation. So we'll use some simple trig. We know that the projected tolerance zone is 15 millimeters, the tolerance zone size is 2 millimeters, and that gives us a possible angular misalignment relative to the perfect axis of 7.595 degrees, which is much larger than the 1 degree that I want. So now we can kind of go backwards and use the trig again to say, okay, well, let's set 1 degree as the target and what orientation tolerances will work for that. And if we're going to do the projected tolerance zone, which is fine, we can just say, well, 15 times 10, 1 degree is a 0.262 orientation tolerance zone. A more rare case, at least for me, and I have seen it misapplied, is tolerancing threaded features at MMC. And when might you want to do this? Let's say, again, you've got some super expensive part and you do your fixed fastener formula and you are only able to squeeze out some small amount of locational tolerance allowance. In that case, it might be worth looking at the pitch diameter size tolerance and assessing how much bonus tolerance could you get from it. And in the case of an M6 by 1 thread, you could get 150 microns of bonus tolerance out of it. So if your options are 20 microns or up to 170 microns, then maybe it is worth adding an MMC modifier to a locational tolerance zone on a threaded feature. Now that being said, I think if you are in this situation, it might be worth considering, can I redesign this part to allow for more locational tolerance on this threaded feature? And something where I think just absolutely do not do it is applying LMC to a threaded feature. The only time I can imagine this being something I might want to do is if I'm working with a pressure vessel or some other thin wall condition. And again, we've got some really tight tolerance zone for some reason, and we need to squeeze out as much locational tolerance as we can. My problem with this is that, one, applying LMC to the pitch diameter is not actually controlling the thin wall condition. The major diameter is what would be the thin wall condition in this case. And as we kind of touched on earlier, it seems difficult, or at least I don't know of an easy way to measure the major diameter of an internal threaded feature. So it really seems like this would be very risky. If your reliability is based off of maintaining some thin wall between a threaded feature and like a pressure boundary, it just seems like it's a recipe for disaster. I would highly, highly recommend, if you are considering putting LMC on a threaded feature, that you try to do a little bit of a redesign. So in conclusion, threads are kind of self-centering with a big asterisk. Typically, you should aim to tolerance your threads at RFS with a projected tolerance zone, and if required, add an orientation control on them as well if it's a high load cyclic application. And if you're considering using MMC or LMC, strongly consider trying to redesign the part so that you don't have to rely on these to make functional parts. Anyways, hopefully this was interesting or educational for you, and have a good one.